Welcome to today's discussion of Chapter 27, More Tests for Averages. And today we will look at the review exercises for Chapter 27. In this chapter, we learn about comparing two independent group means, as in a scenario where you have two samples instead of just one sample, and an expected value. We still treat the hypothesis testing process in the same way. So we still use the hypothesis testing model and steps that we discussed in Chapter 26. We'll get some practice with that today. 500 draws are made at random with replacement from a box of numbered tickets. 276 are positive. Someone tells you that 50% of the tickets in the box show positive numbers. Do you believe it? Yes or no, and explain. Okay, so for this problem, we know that the expected number of positives is 250. Oops. There we go. I've tried to make these a little bit bigger because I realized that your screen shows up pretty small. So do let me know if my writing is too small or you're having trouble seeing what I'm working on. We'll put our model up here. Let's just summarize our model simply to see that it has an expected value. Well, we can simplify this one actually. Let's do it like this. We can simplify it into a box model. This one is actually a one sample test. So we can see here that there's an expected value. Someone tells us that 50% of the tickets show positive numbers. So we know what the expected box looks like. There's tickets with positive numbers and tickets with negative numbers. And we know their proportions. We know that in the expected model, 50% of the tickets have positive numbers, which means that 50% would have negative numbers too in this model. So we can go ahead and state a simple null that let's say it like this, the percentage, because we need to say in our null that what the null always says, that there is no difference either between groups or between the expected and observed values. So here we could say the percent of tickets in the box is 50%. Or sorry, I could actually say this more simply. I started out with kind of a less clear way. Now, this is a common issue when you're trying to write up stat sentences. You shouldn't always just go with what's the first thing that comes to my mind when I'm thinking about this, because oftentimes your mind will go to something that's too much of a that is not stated in language that's common enough, because things should be sensible to people who are generally not statisticians. In this case, we could say that the null hypothesis is that since we should always state it in terms of difference, we should say that the number of tickets, the number of positive tickets in the box is equal to 50%. I really can't write tonight. Why am I writing the null like this? Why not just say 50% of the tickets in the box are positive? Well, that doesn't contain the idea of there being no difference. I'm just trying to state this in terms of the more familiar, this is kind of a weird scenario. The alternative would be that the number of positive tickets in the box is higher than 50, because we should be able to state the alternative hypothesis and just as a restatement of the null hypothesis, except the alternative is one that posits that there is a difference that's not due to chance variation. I simplified the wording slightly just for space. So our terms here, we have an expected value. We would expect, if we're talking about 500 draws, that our expected value is 50% of that, or 250 draws. Positive draws. Let's write that down there. We're also going to need a standard error and a standard deviation to do this problem. We do this similar to the problems in chapter 26. This is a one sample test. We know that we're first going to need to get the standard deviation of the box. The standard deviation we can use the shortcut for. Remember, that's big minus small divided or times the square root of the big fraction times the small fraction. When we do that, the ones and zeros will fall out, so we just get the big fraction expected value would be 0.5 times our smaller fraction expected value, which is also 0.5. And we end up with 0.5 as our standard deviation. 0.5 times. And we can get our standard error with the square root of our number of draws times the standard deviation. So the square root of 500 times 0.5 leads us to a standard error of 11 approximately. And we can go ahead and do our z-test. Observed minus expected over the standard error. Our observed value is 276. The expected value is 250. And the standard error was 0.5. When you work this out, we end up with an observed number that's 2.4. Our z-test is 2.4. So that tells us it's 2.4 standard errors above the mean. It's visualized on a normal distribution. We can see it out here. And we need to, in order to answer their question, do you believe it? We need to decide, is this z-test significant? Is this result just, is this difference due to chance variation alone, or is something else going on? If this result is statistically significant, that will tell us that there's something else going on, that it's not just chance variation. In order to decide if this is statistically significant, you can look up the probability of this p-value in your in a z table, and it's definitely less than 5%. Let's remember that, the decision rule for these tests. If if your p-value is less than if it's less than 5%, then significant. Yes, correct. This is where many investigators draw the line for statistical significance at 5%, which is approximately a z-score of 2. Oh my gosh, I'm sorry, I don't know what's wrong with my fingers today. 5%, and this whole area beyond a z-score of 2 is equal to 5%. So that's a z-score that is greater than 2 has a smaller probability than 5%. So we can say that this result is statistically significant. The p is less than 5%. And will we retain or reject the null hypothesis then? Is this chance variation? Was the number of tickets in the box equal to 50%? Or the number of positive tickets? Reject. Yes, we would reject this null hypothesis because we have such a significant p-value, or a significant one. And so do we believe that 50% of the tickets in the box show positive numbers? No. More than 50% of the tickets in the box, but I'm going to leave that out here just for space. More than 50% of tickets showed a positive number. This was actually 276, that's about 55% of the tickets. And to complete our sentence, we should put in the z equals 2.4 and that the p is less. Oh my gosh. So, what the heck? It's less than 5%. I apparently can't write this out correctly. Now we should have this at the end of the sentence, but I've run out of room. Okay, so a nice hypothesis testing model. Now, with most of these questions in this whole unit, they require a hypothesis test. That's the point of the whole chapter, is testing hypotheses. So when you read a scenario like this where it says, do you believe it? You should think, okay, how can I evaluate if I believe this or not? Probably a hypothesis test. What's the right kind of hypothesis test? And then, of course, do the test. But choosing the right test is the key first step. The Gallup poll asks respondents how they would rate the honesty and ethical standards of people in different fields: very high, high, average, low, or very low. The percentage who rated clergy very high or high dropped from 60% in 2000 to 54% in 2005. This may have been due to scandals involving sex abuse, or it may have been due to chance variation. We're assuming they're simple random samples. Should you make a 1 sample z-test or a 2 sample z-test? What do you think out there? In this case, we have actually a 2 sample test because there are 2 boxes. And I know we saw it's a 1 sample test where we had 2 different years of data, but those were from a population study. So we could compare 1 year to the expected value based on the other year. In this one, it's a 2 sample test because you assume that the results are based on independent random samples of 1,000 persons in each year. So it's not a population level test. They just independently get 1,000 people each year and have them rate how they would rate honesty and ethical standards. So there's 2 boxes. One is 2000. The other is 2005. Each person has, there's the, so if we just think about one of the boxes, each box has a ticket for each person in the population, marked 1 for those who would rate clergymen very high or high, and zero for otherwise, any other thing. Yes, this is high or very high, but and this other, the 2005 box looks the same. The null hypothesis says that the percentage of ones in the 2000 box, or let's set it up with the 2005 box, is the same as the percentage of ones in the 2000 box. So our alternative hypothesis would say that the percentage of ones in the 2005 box is smaller. And I'm just going to abbreviate our alternative hypothesis here, which would say it's smaller. So it's saying there's a difference, and this is the direction of the difference. Let's think about our terms now. We're going to need the SD for 2005 and the SE. And similarly, we're going to need these statistics for the 2000 data. We do have some more in the analysis, but we'll put our test statistic over here. So let's look at getting the SD 2005. You can estimate this from the data. We have these percentages reported, so I'm just using the percentages reported in the problem. This is a 0, 1 box, so the zeros and ones will drop out, and we can get this from the actual 2005 data. And we end up with an SD of about 0.5. Oops. Thus, the SE for 2005 is the square root of the number of draws. There's 1,000 draws times our standard deviation 0.5 for an SE of about 16. We repeat this process for our 2000 data. We'll move it up here because we don't have much space on this one. We get our SD for 2000 by using the proportions like we did before. We have 0.6 and 0.4. Did this all in one step earlier. So we get a standard deviation of 0.49 and our standard error, the square root of 1,000 times our standard deviation for about So I'm sorry, I'm going to back up just a minute because this is obviously, I jumped ahead and, oh, what did I do now? Okay. So our SE percent is 16. I jumped ahead. It's so obviously the standard error itself is 50, and then we can't. Oh my gosh, something is wrong with my tablet. A moment. There we go. Okay. So this is 100 times 0.5, 50, but we can convert that to a percent. So we can figure out the number of respondents who reported that they had very high high or very high you did get 15.8. Gosh, what happened? Oh, yeah, I see what I did. That's why I was just looking funny. I did this right in my notes, but I keep writing things wrong today. You're right. Thank you so much, Stephen. I don't know what is wrong with my fingers today. So let me, oh my gosh. I don't like jumping into these without doing the lecture first. I mean, we did do it. Obviously, we did it yesterday. So it is about 16, and I didn't, oh my gosh, you're right. Okay. I was thinking in my mind about the square root of 100. I did this earlier all correctly, and then I started thinking about, sorry, I'm tired too. I know we're all tired. So sorry. Let me pause here. Yes, 15. All right. So I got 15.5. I'll just stick with 15 because we had 16 for the other. We could convert these into percents. This is what I was thinking about to get the standard error percent, and then this would correspond to a percent of 1.6%. You just divide these by 100. And then the SE percentage for 2000 would be 1.5%. Where did my number go? So we can get the SE for the difference, which is the goal here, because when we get the SE for the percent, we need to get the, as you recall, it's computed from the square root law. So we have our a squared plus b squared Oh my gosh. I don't know what is wrong with me today. A squared plus B squared. I was doing all those chi-squares earlier. It's got my mind addled. And you do need to put these into percentage terms here. Yes. So that 16 is 1.6% squared plus 1.5 squared, and it gives us approximately 2.2%. Why do we have to use percents in this standard error? Because what we're looking at here are percents. We have in our sample the percentage who rated the clergy very high, and we're testing the percentages as frequency counts. So that's why we have to use percentages in our standard error. Thus, the observed difference, so we can do our test here, our observed minus expected. We have our standard error. Our observed was 54%. And this enables us to keep things in percents all the way through. And we get a value of negative 2.7. So we have our value of negative 2.7 here. And is that going to be statistically significant? Is negative 2.7 a z-score that has a probability of less than 5%? You should try this, even if you haven't been doing the math along with me. This part's essential. Being able to make this decision is key for the exam, because you'll get the result instead of having to every time go through all these calculations, but then you have to interpret the result correctly. This is really essential. So it's statistically significant. Thank you. And is that telling us that we should reject or retain the null? We should reject the null. A significant p-value always means reject the null hypothesis. And the null hypothesis says that the difference can be explained as chance variation. That's all what the meaning is here. So there's just the difference is chance variation. So the difference cannot be explained by chance variation. Do we know, was it the scandals? No, we can't know that. We can't know if it was the scandals or something else. We just know that this is not chance variation. In fact, it's true that the percentage who rated clergy very high or high was lower in 2005 than in 2000. And incidentally, that is how I would summarize this sentence too. I don't have space to write it out, but note that we can sort of reword this phrasing here. We can't always do that from a research scenario, but we could say, I just said the percentage who rated clergy very high or high. This is the variable. This is what we measured. Dropped, or we stated and said is to say, because now we know it didn't just drop, which could be due to chance. Now we know it is lower statistically. So we know it's lower in 2005 than in 2000. I moved this around because that's what our test did. We tested if it was lower in 2005 than 2007 or 2000. Okay. Let's try another problem. And I'm just going to walk through the hypothesis testing process, but I'll do just give you the numbers for the calculations and we can practice making the decision. You know, the stuff that really matters for the future of your exam and time management. One experiment involved 383 students at the University of British Columbia. 2,000 were chosen at random to get item A, and 92 of them answered yes. The other 183 got item B, and down here, 161 of the second group answered yes. And so we have these two scenarios. In item A, you imagine you've decided to see a play, pay the admission price of $20 per ticket. As you enter the theater, you discover you've lost the ticket, the seat was not marked, and the ticket can't be recovered. Would you pay $20 for another ticket? And you compare that to another scenario where you imagine, similarly, you decided to see the play, and as you enter the theater, you discover you have lost a $20 bill. Would you still pay $20 for a ticket in the play? From economic theory, both items present the same facts and call for the same answer. And so we would say from that perspective, any difference between them must be due to chance. But from a psychological point of view, the framing of the question is expected to influence the answer. And in this case, we can find out what the data would say. What kind of test would we do here? To tell us what do the data say, you tell me what test. A one sample or a two sample? Yeah, we clearly have two samples here. We have 200 students chosen at random to get one item, 183 get a different item. And so these are independent groups. So this is a two sample z-test. And in this one, each subject has two possible responses, one to item A and one to item B. The investigators only observe one of the two, and the observation is chosen at random. This is like the box model we looked at earlier in this chapter, where you could have observed either response. You only get to observe the response under the condition they were assigned to, essentially, to simplify. And to make the test, you pretend you have two independent random samples. So with item A, the percentage who answer yes, I'll put the data over here, is 46%. This is our expected value, or not the expected value, excuse me, our observed value for this group. And the standard error for the A group is 3.5%. For the B group, the percentage of yeses is 88%, and the standard error is 2.4%. We need to get, to do this test, the difference in the percentages. So we take A minus B, which is 46 minus 88. So our difference is negative 42%. Now, negative 42%, we know that's not a valid percent, but it is in the context of this test because it's just a sub feature of the test. We also need to get our standard error, and we can compute it through our standard error formula. The standard error of the difference is remember, we have to use the square root of our values here. So we have 3.5% squared times plus, 2.4% squared, which gives us a standard error difference of 4.2%. Our test then is negative 42 over 4.2%. So this is negative 10. Is a Z value of negative 10 statistically significant? Will we retain or reject? We didn't write out the null hypothesis, but the null hypothesis would be that the percentage of participants who answer yes for item A is the same as the percentage who answer yes for item B. So are we going to reject or retain? You decide, are we going to reject or retain here? Very good. We are going to reject here. Remember, a Z of negative 10 is extremely improbable. You can plot that Z on a normal distribution if you need to visualize it. And remember that a Z score of 2 is our cutoff for 5%. So Z score of 10 is way down here, so it's clearly less than 5%. Exactly. It's also less than 1%, so we can say it's highly significant. We can write out a sentence here to say that we need to frame our sentence. Remember that we have 88% who said yes to B, but only 46% who said yes to A. Well, our Z-score is negative, so we were looking at the whether the proportions here, and we could say that we frame it in terms of the direction of our test. Fewer, since we did A minus B, fewer participants answered yes to A, and that percentage is 46%, than B, and that was 88%, comma, our Z is 10, negative 10, and we can just say our P is less than 1%. You don't need to give, if it's less than 1%, you don't need to give an exact p-value. Our table doesn't give exact p-values that low, so it's enough to just say that it's less than 1%. Okay? Sentences for this type of problem. Usually easy to write because you're just comparing two groups. Oh. When convicts are released from prison, they have no money and there is a high rate of recidivism. The released prisoners return to crime and are arrested again. Would providing income support to ex-convicts during the first months after their release from prison reduce recidivism? The Department of Labor ran a randomized controlled experiment to find out. So that's important information we should take note of right away. They ran a randomized controlled experiment. So we know there was random assignment to groups, and this is an experiment, so there's two groups, right? The experiment was done on a selected group of convicts being released from certain prisons in Texas and Georgia. Here are our groups. Income support was provided, like unemployment insurance, and there was a control group which received no payment, and 4 different treatment groups with slightly different amounts paid. And we just look at Georgia. Oh, I mean, these aren't our groups. We actually, that's right. This one uses a slightly more complex design that they tell you about and then simplify. So they selected from Texas and Georgia because they didn't want to have results that seem state specific. And within Texas and Georgia, there's both all 5 groups. And they combined our 4 treatment groups into one. Assume the prisoners were randomized to treatment or control. And here we have in part A, 592 prisoners assigned to the treatment, and 48.3% were rearrested during 1 year of release. 154 were assigned to the control, and 49.4% were arrested within a year of release. So how do we determine if income support reduced recidivism? What kind of test will we do? Well, we've only talked about, we talked specifically about how the 2 sample test can be used for experiments when there's a randomized controlled trial and random assignment to groups. We have 2 groups, so we can use a 2 sample test. Incidentally, you could, not using a z-test, but you could, without combining the 4 treatment groups into one, you could look at the 4 groups and the all 5 in one test called an ANOVA. I'm just telling you this so that when you're out in the world, because you will encounter ANOVAs, you realize that would allow comparison of 3 or more group means. independent groups, although there is a related groups test too. We aren't really talking about related group tests in this. So, but you will encounter this when you're reading the literature, and just realize that it's conceptually similar in terms of the function to our z-test for group means or our t-test. It just does, but it can't tell you the direction of the difference because there's multiple groups. It'll tell you if there is a difference among the groups. Here we have collapsed it down to 2 groups. And this kind of thing is a common practice too, because we might be interested in just, did this, any form of this treatment work compared to the control? So again, we have a 2 sample test here. And our null hypothesis is that participants in the treatment group, which I'm just abbreviating as TX, were rearrested at the same rate as participants in the control group. Okay, our null hypothesis would say that participants in the treatment group were rearrested at a lower rate. Why are we interested in that direction? Well, because we want to know if there's an effect of this treatment. So we can get our terms here. The SE for the treatment percent is 2%. And the SE for the control group is 4%. And the SE for the difference is 4.5%. Our observed difference, if we subtract our groups here, is 1.1%. So we can see this is very small. It's just a fraction of a standard error, but we can do our formal test anyway and see that our observed difference over our standard error of the difference if you look at it in rate form, you can see this is clearly not going to be significant. And it, in fact, gives us a z-score of 0.24. I've kind of given away the end already, but are we going to retain or reject based on this z-score of 0.24? Will we retain or reject this hypothesis? Yes, we will retain, because remember, our z-score of 2 is where 5%. So a z-score of 0.24, it's way over here. It's almost at the mean. So we'll have to retain. And we would say that the treatment group, it would be better to say the participants in the treatment group, but I'm just working with space here. The treatment group was rearrested (48.3%) at the same rate as the control group. Z equals 0.24, and we can just say, I mean, you could give the exact p value. Rather than take the time to look it up, I'm just going to say that the p is greater than 5%. Okay. So did income support reduce recidivism? No. And we would say no. And the explanation is the sentence we already wrote. There's a second part here. In the first year after their release from prison, those assigned to the treatment group averaged 16.8 weeks of paid work. The SD was 15.9 weeks. For those assigned to the control group, the average was 24.3 weeks, and the SD was 17.3 weeks. Now we could look at, did income support reduce the amount that the convicts worked? And this, we clearly don't have space to do here. Let me adjust that for us. We'll work it out. So this is item 7 continued. And I'll give you the values here. So the SE for the treatment, actually jumping ahead a little bit, let's think about what we're testing here. So we have our, this is clearly going to be another 2-sample z-test. We have the same groups, but they have, now we're looking at the amount that they worked. So we can write our null hypothesis. which would say there's no difference between the groups, right? The treatment group worked the same number of weeks as the control group. And notice how my null hypothesis sentences usually are very similar to the results sentence, except you can rephrase it to, express the results. If we find no difference, this will be a sufficient result sentence when we put in our values. If we reject the null, then we need to restate this to state the difference. The relevant statistics to get here are the SE for the treatment group, which is 7.7 weeks. There were some more values given in the problem that I'll transfer over in a moment. The SE for the control group was 1.4 weeks. And if you get the difference in the previous, from the scenario, you can see that the observed difference is 1.6 weeks. Oh, not the observed difference, the standard error of the difference. Am I writing? And our observed difference is negative 7.5 weeks. That's just based on the values in the problem. Oh no, crap. Oh. So our z-test is just our observed difference over the standard error of the difference, or negative 7.5 over 1.6, and we end up with a z of 4.7. So you decide, was there an effect of, did the treatment have an effect on the number of hours worked? Specifically, we looked at, did the treatment reduce the number of hours worked? And yes, we did find that. So we can see this on a normal distribution, remembering that 2 is the critical value here. 4.7 are so the difference is real, and we can see that it should actually be negative. It doesn't matter. The distribution is symmetrical. So we know we are going to reject the null. So we can translate our null hypothesis into a good sentence. The treatment group What did they do? Well, we know they worked fewer hours or fewer weeks. And we should put the mean number, the mean weeks worked here. And that was in the problem, 16.8 weeks. Oh my gosh. The control group worked 24.3 weeks. You can write mean in here too. I'm just trying to conserve space. And our Z is 4.7. And the P is definitely less than 0.1. Which is, or 0.01 or 1%. Okay. And let's see. One more problem. A researcher wants to see if the editors of the journals in the field of social work are biased. He makes up two versions of an article in which an asthmatic child was temporarily separated from its parents in an effort to relieve the symptoms of an illness that is often psychosomatic. Okay, in one version, the separation has a positive effect, in another, negative. The article is submitted to a group of 107 journals. 53 are chosen at random to get the positive version, and 54 get the negative one. And we have their results here. And the first column of the table says that 28 of the journals getting the positive version accepted it for publication, and 25 rejected it. See, they got the positive version. The second column gives the results for the journals that got the negative version. Is chance a good explanation for the results? Well, what kind of test are we going to do here? This is clearly a two-group test. I think you should see that. There's two groups. But the question is, what are we going to compare about them? And we need to turn this data into proportions or percentages in order to use it in our problem, in our solution. So I'll just, to do this easily, expand things over here. So we have a positive and a negative, and the proportion accepted will make our box model acceptance rate, right? The proportion accepted is 28 out of 53, the total. And it's going to be 52.8%. And the negative group we get in a similar fashion, it's 14.8%. I'll put the SEs over here too. This is such a helpful table. So our SEs are 6.9 and 4.8. Let's make sure to state our null hypothesis, which would be that the journal acceptance rate. We would say that journals accepted the positive effect article at the same rate as the negative effect article. Okay, so we can take a look at the difference between the groups here. We can, you can just get this difference by subtracting them. So our difference is 38%. And the SE for the difference is 8.4%. Oh, 8.4%. My brain is really not connected to my hand tonight. Jeez. So our test, we've got Z, our observed difference over the standard error for the difference. Our observed difference was 38%. Out of our standard error of the difference, 8.4%, which yields us a Z score of 4.5. So if Z is equal to 4.5, will we retain or reject the null hypothesis? That's right, we're going to reject. And what does that mean? Well, it means that this difference is not due to chance alone. Chance is not a good explanation for the results. We know that, so we can, since that was in the question, we answer that part first. Chance is not a good explanation. What can be concluded about the journal publication policy? That's our standard results sentence. We would say that journals accepted the positive effect article at a higher rate than the negative effect article. And then give the acceptance rate for that one, 14.8%, comma, Z equals 4.5. P is less than 1%. And when you write up results for the exam, I'll be looking for sentences that always fit the same format that we've been doing each time, where you state the effect, the direction of the effect if possible, the relevant summary values, and the test statistic and the p-value. And we're going to skip item 11. It's too long. You can skip it too if you want in your homework. Whew, we need a little break. The main point to take away from this material is to practice making sure you're getting the test choice right, and then the decision process for retaining or rejecting the null. As you can see, the calculations are basically the same for all of these. We did one example of each type of problem, or a couple of the one type. And the important piece is to always use the hypothesis testing model to organize your approach, and that will help you get at a correct outcome more often.